Howdy doody, students. We are into chapter 5. And with all the power outages on campus, I'm not sure when we're going to come back, to be perfectly honest. So I want to make sure you have at least some videos that'll kind of help walk you through the key ideas. This chapter only has 2 sections, just one section that includes both addition and subtraction, and one section that includes multiplication and division. Now, this section is all about a new set of numbers called integers. And we've already dealt with the whole numbers, so we got an idea of what those are. And let's take a look and kind of say, well, let's make sure we understand integers. So we've got our Common Core state standards listed here. Understanding positive and negative numbers that are used to describe quantities, temperatures above and below zero, elevation above and below sea level, credits or debits, like maybe money or bank account, positive or negative electric charge, and understanding what zero represents. So in the past, you got to remember, we just came out of a section on whole numbers. And if someone had said, hey, I'd like to find this result. I'd like to find what happens when I do 4 minus 6. We would have had to answer that question and say that the answer is not a whole number. And depending on where you're at in the curriculum, this is the perfect way to do it. And that's because what we're looking for is a particular number that we add to the number 6 and we end up at 4. Now, this violates what we know about whole numbers, because a whole number, when I add 2 whole numbers together, the result is either the same or larger. But in this case, as we can see, the result got smaller. So we start by saying it's not a whole number. And then what we do is we kind of say, well, I wonder if there's another group of numbers where it could actually exist. And that's what we need to do. We just need to invent a new number that's very similar to 2. So it's almost like I want to take 6 and add 2, but I need to add 2 that's kind of going the opposite direction. And so we add what we refer to as -2. So this might be our first introduction to negative numbers. And that's the idea. Now you can see where -2 would live on a number line right over here. And again, we have kind of the same concepts with positive, positive and negative. So when we're thinking about all these numbers, we have the whole numbers, which include 0, and they go to the right. Then we have these numbers that go to the left. So 0 is really kind of a very interesting number. 0 is not positive, it's not negative. Okay, so everything else, though, you could think of it as being +2 or -2, meaning to the right of 0 on a number line or to the left of 0. And I think that's the important piece as we go forward, is kind of understanding what's that big idea about these. So the way we tend to define the integers is the union of negative integers, the set of positive integers, and the set 0 is the set of integers. Frequently, this is referred to as the set of whole numbers and their opposites. So a whole number would be any of the numbers that we kind of think about as being whole numbers, any of these pieces, 0, 1, 2, 3, and 4. And then we would have the opposite. Now, the fun fact is the opposite of 0 is still 0, but the opposite of 1 would be -1. The opposite of 2 would be -2. So you could also think about this as being the whole numbers and their opposites. So that's kind of a way, kind of a slang way to think about this. Because otherwise, it's not ideal. I mean, you could technically think of these as you call them negative integers, but we're already using the word integer. This is why I don't really like the way that the book has defined this set, because what is the set of integers? You've already used the word integer twice to define the set of integers. So not my favorite use. I think it's unfortunate. I prefer the older editions of the book where they didn't have this glaring glaring issue. All right, well, let's jump into it. So anyway, the goal of that first section is actually, before we even start 5.1, was to kind of say, hey, let's talk about what an integer is. Now that we know what an integer is, let's now talk about what we have. So you can see here the word that I used before, the opposite. Negative integers are the opposite of a positive integer. We can also think of as those negative values are the opposite of a whole number, a positive whole number, if you will. So the opposite of 5 is -5. The opposite of 0, you can kind of think, when I think about it, I think opposite as being like a distance. So same distance away from 0, but just in a different direction. So 5, I would move to the right 5 units. -5, I'd move to the left 5 units. But both of them involve the idea of 5. Okay, so finding the opposite. So one thing as we kind of go through is if you have a number like 3, you can picture it on a number line. The opposite would be, you guessed it, -3. And then here for -5, the opposite of this, which is the opposite of -5, that's how we're kind of reading this. This really is not the same. Some people might say negative times a negative is a positive. That is not what this is. This is the opposite of -5. And the opposite of -5 is +5. Okay. So let's talk about this then. What kind of operations do we have as we take a look? Oh, and this is a great little note here historically. So if you haven't heard about this story, there was kind of a mathematician, and his name was Al-Khwarizmi. Now, Al-Khwarizmi uh, kind of indicated negative numbers. He did it differently. Instead of the little symbol out in front, he put it with a little circle over it to kind of indicate, hey, this is like that quantity just going the other direction. And sometimes in the number was utilized on bags of things that were being shipped, bags of grain, barrels of wine, or anything else. And what they would do is they would measure it, and they would say, oh, this one is above. Maybe we say this bags of flour is supposed to be 50 pounds. Well, when we put it on a measuring device, it turns out to be 52. So they would actually write on the top of the bag of grain +2, indicating it's 2 higher than we thought it was. It could be also a pound under, and you would write -1, or I'm below the amount by 1. And that kind of gave us kind of some of these pieces as well. In any case, Al-Khwarizmi, his name, if you say it fast, is kind of where we got the word algorithm. Al-Khwarizmi. He was creating processes to solve problems. And so we have the idea of an algorithm that came from him. All right, school book page on integers. There we go. Oh yeah, an absolute value. The reason absolute value is so important is absolute value talks about a distance. And distance is always positive or 0. So distance can never be negative. So when we talk about distance, when we say absolute value, we're almost always referring to the distance from 0. So when it says absolute value, and again, this from your past math classes, if it says absolute value of 5, what we're saying is, here I am standing at 5. How far is it to get to 0? And you could write down, oh, okay, that's 1, 2, 3, 4, 5 steps. Got it. So it's 5 steps. If I wrote the absolute value of -5, well, how far is it from -5 to 0? Well, you notice it's going to be 1, 2, 3, 4, 5 steps. So again, the absolute value is distance, and it is almost always a positive number. However, if you were living right on 0, then the absolute value of 0 does equal 0. Like, what's my distance to 0? And someone would say, you're standing right on top of it. The distance is 0 units. Don't move. You're already there. That's the idea behind the absolute value of 0. Okay. So what we do is we have a definition down here. And this definition, for some students, I think it makes, it looks a little confusing, because what we're saying is we have a conditional definition. You see, if x is greater than or equal to 0, then the absolute value equals itself. Well, let's take a look. So absolute value of 7, right? Check. If x is greater than or equal to 0. Okay, so 7 is greater than or equal to 0. Then the absolute value of x equals x. So just equals the number itself. Perfect. But notice this second condition. This is the one I think that gets people. If x is less than 0. Okay, so now if I do the absolute value of -7, then what is my result? My result, the absolute value of -7 would equal the opposite of x. So I would write the opposite of -7. And remember, the opposite of -7 turns out to be +7. And I think, now this is just from my history teaching, I believe most students, when they see this symbol written like that, they think, aha, that is a negative. So they would even say the word negative x. I'm going to try to push you not to say that. And the reason is we don't know whether x is positive or negative. So we shouldn't say negative x because then our mind is thinking it's a negative number. What we should say instead of negative is the opposite of x. Now, if you say the opposite of x in your mind, if x was positive, then the opposite would be negative. If x was negative, then the opposite would be positive. So that's the idea in understanding that kind of terminology there. I think it's good to know. It's good to know those. So they do a little bit with absolute value here, absolute value of 0, absolute value -5, absolute value 20. This is a fun one when they start saying the absolute value equals 3. And if you think back to what I just said about the definition, if the absolute value of x is equal to, let's say 5 here, right? Absolute value of x is 5. What does that mean right here? The distance to 0, that's what that means, is 5. So on a number line, here's 0, but my distance to 0 had to be 5. So that means I could have been 5 units up here, or I could have been 5 units down here. And so that's why my answer to this, if I was solving this, I would say, well, x could be 5 or -5, either one of those. Okay. Again, algebraically, this is probably one. Part E is where I think some students do run into trouble because of their past experiences. And so let me just kind of briefly say something. When we're talking about the distance plus -5, that distance has to equal 1. What we're really saying is whatever this object is, x plus -5, it could equal +1, right? Or x plus -5 could equal -1. So you really have two things that you have to do and two equations that you need to solve. But all of that, I'm going to change color here, all of that comes back to just thinking, what if I said the absolute value of something equals 1, right? Well, I mean, that thing could have been +1. That thing could have been -1, right? And so all I'm doing down here is I'm just taking the thing and saying it equals 1, or I'm saying the thing equals -1. So you have two completely different options there. So that's the thought process behind these. I think the most, probably most frustrating for students because they get things wrong quickly is they say the absolute value of x plus -5 equals 1. And then they'll add 5 to each side to be like, let me balance it out. And now I've got absolute value of x. Yes and well, and completely no, because what you're changing is it's this entire quantity's distance has to be 1. And once you add 5 to both sides, you're changing what we're looking at. The distance from a particular number to 0 has to be 6. But that's not what the initial one said. So what I'd recommend is when you have absolute values equal a number, that you say, wait a minute, what could go in there to equal that number? And it's almost always that number on the positive side and that number on the negative side. So positive x, +3, -3, stuff like that. Okay. Yeah, I don't think I want to say too much about this. Understanding that a negative balance can be thought of as debt. For you, kind of where you're at in your life, I don't think I'm going to go too far with that one. All right, next up, how do we represent integers? We already had representation of whole numbers, especially with addition, subtraction, and so on. And now we're going to use representation with chips. And the idea The biggest piece here is to understand the concept of a zero pair. And a zero pair is simply something that equals 0. So if I put a positive with a negative, you can think of these as in like a chemistry class, you put these two together, the overall charge is 0. So this would be considered a zero pair. And you can actually see zero pairs like this right here. So when you look at those, a positive with a negative, they basically cross each other out. However, value-wise, the value of the overall piece doesn't change. There's more chips being used, but many of them cancel each other out. So the quickest way to write +2 would be with 2 positive chips. But you could also write it with more chips if you just add a 0 pair. And you could add another 0 pair. So now there's 2 0 pairs being added. Okay. Now this is this is a really important, I'm going to put, yes, you need to know how to do this. There will be a question on the exam about the chip model because the chip model is one of the easiest ways to represent integer addition and subtraction. And we don't have the issues with the chip model that I'm about to show you with the number line model. So let me jump down to the number line model. Number line model. Here's the rules for walking the number line, all right? So if start at 0 and you always face the positive right direction, okay? If the number is positive, walk forward. If the number is negative, walk backwards. So there it is. Now, when they're talking about this, if the number is positive, walk forward. If the number is negative, they're really talking about addition or thinking about the initial number, which is, again is fine. So when you think about addition, you're going to keep going in the same direction, and then you continue with that same idea. If the number is positive that I'm adding, walk forward. If the number is negative, walk backwards. And again, no big issues with that. It says there's other models. Some of the models they say is the charge field model. And the charge field model is just writing a plus sign or a minus sign instead of using a chip that is kind of labeled one way or the other. I think what I'm going to do in class for our activity is going to be to use 2 types of chips, and they're related to business. So for example, if you're in the red in business, it means you're in the hole, which also means negative. And if you're in the black in business, then that means you're doing well. It means your business is in the positive. So if you were to write down BB and an R, then this would still be a 0 pair, and the overall value right here would be the number +1, because I have 1 positive and then a 0 pair sitting next to it. Let's see here. The other one they do is a temperature cube model with red is positive and blue is negative. So like add a degree, kind of add a negative degree in a sense. But I think in terms of usage, probably the charged field model where you write a plus or a minus, probably one of the top ones. But also the colored model seems to work really well, especially for kids who want something that's hands-on. Yeah, that one's hands-on. So integer addition. So again, what are we doing? The first piece that we just talked about is how do I represent an integer? Now we're going to say, how do I represent addition with an integer? And addition is actually really, really nice. I think most of you are probably going to like it. This would be a very quick question on the test because I would say, show me addition. And so if you had the question -4 + 3, you could start with 4 negatives, which we've kind of listed here, and you just kind of put them down. There's 4 negatives. And then you add or you combine together with 3 positives. So -4, and then I add +3, and there they are. And you can see that I've put them together. And then find your 0 pairs, because anytime you have a 0 pair, it equals 0. So 0, 0, 0, and this is -1, and that's why my answer would be -1. So your 0 pairs can be kind of canceled out. Kind of a quick way to think about it. Okay, now here comes the fun. They show this with the idea of a cat walking, and what they say is, Here's the idea. Here's the number line. You stand at 0 facing positive, okay? And I've done this in class where I actually drew a number line on the board. We're missing a whole day, but I don't know if I'll be able to do it. But the idea is that you walk physically in one direction towards the positive, towards the negative, and you walk backwards or forwards. And so if you are this little cat, you start at 0. Then because I want to do 3 plus 5, I would move forward 3 units and then I'd pause. Then I don't change anything, but then I move forward 5 more units. That's because both the numbers are positive. If I was doing -3 plus 5, then I would start by going to -3 first, which means I start at 0, face the positive, because that's my starting point all the time. Then I move backwards 3 units, which kind of do the moonwalk, and then stop there. And then I'm not changing my orientation. I'm still facing the same direction. Now I walk a forward 5 units. Okay. So a couple of those that you could kind of work through and do if you want. And let's see here. There's a thermometer piece. There's a pattern model for addition. This, yes, this is a pattern. What we've seen in the past is that patterns are good. How do I say this? Patterns are good if it works out perfectly. And so that's why I don't like using patterns, is because a pattern is basically a list of examples. And a list of examples is never going to give you why does that continue. So in this case here, what they're doing is saying 4 plus 3, 4 plus 2, 4 plus 1, 4 plus 0. And what they're saying is, oh, look, I can see that the amount is going down by 1 every time. So therefore, I'm going to continue that over here. Yes, that would be inductive reasoning, which means your conclusion isn't always guaranteed. Okay, let's see here. Where would you show this? Oh, if you were doing multiplication, right? Then that would probably be kind of a bad one. For example, right? 0 divided by 4 is 0. 0 divided by 3 is 0. 0 divided by 2 is 0. 0 divided by 1 is 0. And if I use the pattern model, I would look and say, aha, got it. 0 divided by 0 is 0. But we know that that is not true. And this will be my sad face, because that's not true. All right. Well, let's take a look. So again, pattern, if you like it, you want to write out patterns, that's great. But remember, you are making an assumption that the pattern has to continue. And you're also making an assumption that the pattern determines the correct values for what you're doing. And as I just showed you, that's not always the case. All right, so we define integer addition. Yeah. So here's the definition of integer division. All right. It looks very complicated, but in reality, yeah, they're basically going through every possible case. And so as you go through it, you could say if m is any integer, then if you add 0, you get what you started with. And that's just basically saying that's the identity. So we have the identity property again. If m is greater than 0 and m, okay, so if we have two positive numbers, that's right here, then if you add them together, it's defined using addition of whole numbers, because we already did that. We already did two positive numbers like this. But the next one says, what do I do if I have two negative values? So like a -2 plus a -4. If I was using the chip model, I would put in 2 negative chips to start, and then I'd put in 4 more negative chips, and that would leave me with 6 negative chips. And we could just count them. And to me, that's the quickest way. And that matches up perfectly with what they're saying. They're basically saying, hey, just do what you were doing, but then say it's the opposite of 2 plus 4. Because you know how to do 2 and you know how to do 4. You add them together, you get 6. But when we do negatives, it might seem different. And all they're saying is it's not different. If they are the same sign, like negative and negative, you can simply combine them and get -6. If you have 1 greater than 0 and m is greater than this one. So now this is where things get a little sketchy. At least some students think so. Because now I'm going to say, well, what what if one value is bigger than the other? And I want to add them together with some negatives. I want you to picture this, right? Let's say that I had um, 4 positives, right? And then I'm going to add 3 negatives. Okay. That result of 4 positives added to 3 negatives, 4 plus -3, we actually could say that's the same thing as doing 4 minus 3, because really you'd be kind of taking these away. You can think of it as the comparison model if you prefer. So 4 plus -3 becomes this value. But if you go the other direction, what if I had 4 of these negatives and only 3 of the positives? Well, again, the comparison model still holds. I just need to end with a negative. So this model would be like, okay, hold on. What I want to do is I want to do -4 plus +3. But really what I'm doing is I'm doing 4 values and I want to take away 3 of those values. But whatever you're left with, in this case, which would be 1, I want to make sure it's very clear that that is on the other direction. So the negative in the 4 really ties it together. Okay. I have worked with a number of students, even younger students, who appreciate the idea of just decomposing. And decomposing is a really powerful approach. Let's take a look at decomposing. So if I had -4 plus 3 and a student was struggling with this idea, I would ask them and say, well, wait a minute, if I had 4 negatives, wouldn't that be the same as like a -1 plus a -3? Like you have a -1, you add -3. The issue is usually with the positives and the negatives mixing. And if you're able to kind of say, yes, well, 4 really is 1 plus 3, just like it is with negatives. And then use the associative property because you get a really beautiful thing about 0 pairs. And that is another way that you can get to that same result. Pretty cool, pretty cool. All right. So that's the definition of addition of integers. There's another definition down here which says, can we just use absolute value? Because that way what we can talk about is which number is further away from 0. And it doesn't matter whether it's positive or negative. If they're both positive, then we're in one place, right? If one's positive and one's negative, then it matters which one's further away from 0, because that's going to be the bigger value. That's going to be the one that dominates the other. And so that's really what this is just showing right here. It says if m is bigger than n, so m is positive, n is negative, but the value of n, the distance of n, the absolute value is bigger, then m is going to dominate. And while I do the subtraction, the result will end up being positive. If the negative value, the negative integer, is further away from 0, then when you add a positive to it, you end up getting closer to 0, but not all the way. And that's why you still end up with a negative value. That's what the bottom one shows right here. Let's take a look at the school book page. So what do I have? Negative integers, and additive inverses. Again, additive inverses, also known as opposites. And so we're going to kind of go through these properties here. Properties of integer addition. Guess what? Hopefully these aren't a shock to you. Closure, commutativity, associativity, and the identity property, these still hold the same properties that were there for whole numbers. Next up, this is a new one. This is a theorem, and it says every integer has an opposite. Okay, so this is something new. We couldn't do this with whole numbers. But what we say is, okay, I think that every number has a very special number that I can add to get to 0. Okay? So if I think about that, then I think about, okay, here's my number, right? And whatever number I have, I think they call it a to start with, because I think they say for every integer a. So pick an integer a. So there's the integer I picked. Now this will be my additive inverse. So I'm going to add that to a, and that gets me 0. Okay. All right. So that looks pretty nice, right? Well, let's see here. X plus a is equal to 0. So if that's the case, then that object x is going to be called the opposite of a. Now, some of you again might call that negative a. I'm going to try to push you out of that habit. Don't say negative a. Call it the opposite of a. Okay. But this number down here, negative a, it's an integer. You must be able to add something to it to get back to 0. And the thing that you would add to it must be the opposite. So again, let's take a look what that means. It means the opposite of the opposite of a plus the opposite of a has to give me 0. Okay, so now this is where things get a little bit interesting, because initially x was equal to the opposite of a, which would have told us that the opposite of a plus a gives me 0. But down here at the bottom, I have opposite of a plus another object, and that equals 0. So this is the piece that tells you, hey, guess what? A is equal to the opposite of its opposite. So we can actually say no matter what you do, that thing is actually unique. So any number you can think of, I can think of an additive inverse that I would add to get back to 0. That's the big piece here about additive inverses. Theorem, a, b, and c be any integers. Again, take a look here. The opposite of the opposite equals a. And you can demonstrate that by showing what I just showed, which is if I add a to it, I get 0. If I add the opposite of a to this, I get back to 0. And that is enough to say, well, then those two things have to be equal. This is a fun one, the addition property of equality. Basically, if you take two things that are equal and you add something to both sides, they are still equal. And we use this as the basis for algebra later. We would add something to both sides to solve an equation. Okay. And lastly, down here, this one. And again, this is one that I do enjoy giving as a proof. Not saying it's probably going to be in the homework, but it may also appear on an exam. So again, if you wanted to prove that the opposite of a plus the opposite of b is equal to the opposite of a plus b, we'd have to have some kind of reason why that is. So let's talk about that. And I think, I'm not sure. Let me see if they gave that solution in this version of the textbook. Ah, they did. Okay, well, that's fine then. It's pretty similar to probably what I would have done. And yep. So this is about the uniqueness. And so what we could say is we're trying to show that the opposite of A plus the opposite of B is equal to the opposite of A plus B. Now, a common misconception here is that we can just distribute this. We don't have a property for distributing opposites. We have a property for distributing negative numbers with multiplication. This is not multiplication. It's simply the opposite. So what do I know? I know that a plus b has to have a unique additive inverse that gets me back to 0. And that thing we would call the opposite of a plus b. So now let's take a look what happens if I do a plus b and I add the opposite of a plus the opposite of b. I don't know what I'm going to get, but let's find out. Well, what I could see is I could switch these two around using commutativity. So that would leave me a plus the opposite of a plus b plus the opposite of b. Let's see here. A plus the opposite of a is 0. B plus the opposite of b is 0. And the result then becomes 0. So that means if I bring it all the way up here, a plus b plus this other weird looking thing gives me 0. But I already had a cloud that got me to 0. And that's why these two must be equal. So we would say the opposite of a plus b is equal to the opposite of a plus the opposite of b. So that's how we could prove that it has to be that way for all numbers. Okay, let's here find the additive inverse of following expressions. Just be aware there's more than one way to write some of these. So I want to make that very clear. So right here in part B, it says it can be written as this, it could be written as this, it could be written as what you see up front. So 3 different ways. If you continue on in math classes, what we start to look at is what's the most efficient way to write it. All right, we're going to get into subtraction now. So we just did addition. You can imagine subtraction is very, very similar because it is. We're just going to be taking things away. So in the model that we would see here, we need to model something. And I think this is, again, occasionally students have an issue with this. If I wanted to do 3 and take away -2, I've got a problem. I got a problem because the number 3 is just 3 positives. I need to find 2 negatives that I can remove. In order to do that, we would add in 0 pairs. And the reason I add them in is because they are worth nothing. They are worth 0 as I add them in. I can have as many as I want. And then I say, okay, now that I have them in there, it's still the number 3. But then what I demonstrate is let me circle the 2 negatives and pull those out. So that is the idea here. Now, to be honest, I kind of wish they would have started with something that's just a little tiny bit like, why not start with something to demonstrate this? Why not just do 3 minus 2? Okay, start the picture, draw 3. That's pretty quick. And then put a little picture like this and say, got rid of those 2, and you'd be able to say that that equals 1. All right, so that's a pretty good idea there. Integer chips. Number line for subtraction. Yeah. Subtraction, they say, is modeled by turning around and facing the negative direction. So that if you have a problem like some of these, let's say -3 minus 5, then you would go to -3 first, still facing the forward direction because negative number just says walk backwards. Subtraction means I turn around. Now you're facing the backwards direction, and the 5 is positive, so I would walk forward 5. But remember, now I'm facing the other direction, so I'm actually walking away from 0. So why do I say this has issues? This has issues because unlike the chip model, where addition and subtraction could be recurring at any point in time without an issue, this one I have to be very, very careful because if I did something like 5 minus 3 plus 2, then using the order of operations, I would start by going to 5. I'd go to 5, right? Still facing this direction. Then -3 says, okay, turn around and face the other direction and walk forward 1, 2, 3 units. Okay. And I'm still facing that same direction and I'm at +2. Let's see here, 5, 4, 3, 2, 1. There we go, +2. And then it says +2. Now remember, addition, I don't change anything. I don't change the direction. So I just stay facing in the same direction and I add 2 units. And if I do that, then I end up back here at 0. That's a problem because that's not the actual answer. The actual answer is 4. So if you are using this model, if you like this model, then just make sure every time you complete an operation and you kind of bring down anything else, start over. You have to go back and say, now I'm going to draw a whole new number line and start over with 2 plus 2. Otherwise, you will run into issues, and so will your students. Okay. There's our transactions. Again, they have the pattern approach, which is fantastic. It does make it seem 3 minus 2 is 1, 3 minus 1 is 2, 3 minus 0 is 3. 3 minus -1, if we follow the same pattern, it has to get bigger. And I would say 4 and 5. But again, that doesn't really go well because all it takes is it to fail. And so with this pattern approach, and they even say it here, they say by using inductive reasoning. The minute you say by using inductive reasoning, you are creating a situation where you may not be able to say you're correct. Oh, let's see here, integer subtraction. You know what? This is what's great about subtraction. It's the same concept. So a minus b is the unique integer. We used to call it the unique whole number, but now we're dealing with integers, so we have to kind of change that. The unique integer such that a is equal to b plus n. That's right. What is called the difference between two numbers is the subtraction piece, as long as you can check it with addition. Okay, so there we go. All right, let's take a look. Theorem 5-4. For all integers a and b, a minus b is equal to a plus the opposite of b. Is this always the case? And the theorem basically says it is always the case, but why? So again, if you want to, which is kind of the idea, right? Yeah, you absolutely could come through and say, all right, let's take a look at this. How do I know for certain? And you can plug in a few numbers to kind of check yourself. And it seems like it always works. And you could actually, we're going to illustrate this with the chips when we come back next week. But in order to show what this is, we know that a minus b is equal to some number as long as, if and only if, b plus c equals that number. So it says, we believe that a minus b, which is this cloudy thing, is actually equal to a plus the opposite of b. So now I'm going to check that, because I'm going to come over here and I'm going to say, well, let's do b plus whatever I got here, a plus the opposite of b, and then do this commutative property and associative property, because what you're going to get is that the b goes away, b and negative b with the commutativity. And what does that leave me with? It equals a. And that's exactly what we were trying to show. So yeah, since it goes back and equals a, then that means b minus a is equal to a plus the opposite of b. Really interesting way of thinking about subtraction now. Basically, every time you see subtraction, you could rewrite it as addition. And sometimes you probably did this, but other times you probably did not. So again, in prior courses, a teacher might have said 2 plus -8. Hey, just rewrite, oops, 2 minus -8. Sorry about that. 2 minus -8. And you say, okay, rewrite that. So if I rewrite it using what we talked about up here, the subtraction is equal to adding the opposite. So 2 plus the opposite of this, which I will write as the opposite of -8, which means I really have 2 plus 8, which means I really have 10. All right, rewrite without parentheses. Now I'll let you do a little bit of algebra on that. And I think we're right at the end of the chapter. Yeah, be careful with your calculator. Depending on your calculator, it may have a subtraction symbol and a negative button. They may not actually be the same, so you want to be pretty careful with those. So yeah, 2 minus 5 minus 5, you could put that in. But again, if you had a negative, make sure that you you know how to type the negative in on your calculator or your cell phone. I think some cell phones do allow you to do negatives. And that wraps it up. That wraps it up for 5-1. I'll go over some of the homework problems in a separate video. Hopefully that gets you kind of the big idea here. What I liked about this section is, hey, the definitions really aren't anything new. They're the same thing we've been doing before. So no big worries there. Now we're just applying them to different looking numbers. And when you start doing subtraction with integers, again, subtracting negatives is something that really can get inside of a student's head. Just remind them, you can always rewrite it as adding the opposite. It's like your best friend. All right, that's it for now. Hopefully everything's going good. And hopefully the power comes back on. All right, thanks a lot. Off you go.